Okay, maybe we'll begin. Welcome, everybody. My name is Leah Radzikowski. I'm a professor here in physics. And as the host of this event, it gives me great pleasure to welcome you all here and introduce tonight's speaker. But before I do that, I wanted to just say a few words about the background to this event. If you're new to these events, this is an outreach effort of the so-called Boulder Summer School Institute that we hold here on campus every July for 4 weeks. It's a school, so-called school, advanced school, in which every year we have about 65 students and postdocs from all over the world come to Boulder campus, stay on campus for 4 weeks, and attend lectures that are given by sort of world-renowned experts, professors from all over the world on the subject of a school. And each year the school subject varies. The schools are supported by the National Science Foundation and also in part by the physics department from University of Colorado. And so it's really it's also, this lecture is kind of in part, your tax dollars at work, trying to share in the excitement of the physics that's covered in these schools. So in the past, as I said, schools are varying topics and they range. This is a 25th school, so we started in 2000, and except for the COVID year, have had it on this campus every year. And schools have ranged from really diverse topics in materials, advanced material science and condensed matter physics, from superconductivity to biophysics to quantum information to magnetism, and across the board. It's very extremely broad. And we have some students in the audience. If you're the best and brightest coming from attending the school, can I see a show of hands? Maybe, okay, it's not so many, but they're tired from all the lectures they've been attending for the last 3 weeks. We're in the 3rd week of the school. And so, this year's school is on so-called quantum dynamics of strongly correlated systems. So it's sort of a frontier, exotic topic in quantum mechanics, if you wish. And it's at the heart of understanding and search for exotic materials of the future, where one studies dynamics of electrons, protons, phonons, and all kinds of other things in materials. So with that, let me turn to tonight's speaker. It's a great pleasure to introduce my colleague, a distinguished professor of physics, Margaret Murnane. Margaret was born and raised in Ireland and came to US to Berkeley for a PhD. Her PhD is from Berkeley, UC Berkeley. She then spent, I won't spend time talking about various other places that she was a professor, but eventually she came to Boulder in 1999 and built a world-leading group in laser science together with her husband, Henry Captain, who is sitting over there. So Margaret is really a world leader in the subject of laser science, and in that she studies, laser science is a broad field that ranges from is of interest to studying materials, plasma physics, nanoscience, but her focus is on generating ultra short pulses, very intense laser pulses, and using them to really create X-ray laser sources, and then use those X-ray laser sources to study materials and quantum dynamics in materials, and hence the relation to this year's summer school. Being a leader in this field, really a world-recognized leader, Margaret's been recognized by many awards. If I went through all those awards, we'd probably take good fraction of an hour listing those awards. So I'll just mention a few of those. She's a MacArthur Fellow, so-called the Genius Award. She's the recipient of Benjamin Franklin Medal of Physics, Arthur Schawlow Prize in Laser Science, Isaac Newton Medal, and she's also a member of National Academy of Science. And so tonight she'll be speaking about building a quantum microscope of the future. And with this, please join me in welcoming Margaret.
Thank you so much, Leo, for allowing me to be part of the summer school. Teaching is every bit as much a passion as doing research on this crazy quantum phenomena. So it's a real pleasure to be here this evening, and thank you for coming out. So this topic of trying to figure out how to build the best possible microscope is really hard. We cannot do it alone. So it would not be possible without an amazing team of graduate students and staff who help us, do the research, also collaborators and many alumni and collaborators from all over the world. So I'll try to tell you a story of how this topic, some of it started in the Star Wars era that some of you might remember under the Reagan administration, and how that eventually led us to new quantum light sources and now quantum microscopes that can help us try to build the ultimate light-based microscope. And I'll try and explain why on earth do we want to do that. And then here are pictures of some of the students who've worked with us over the years, and we're really proud of them. And many of them are working here in Colorado now. Okay, so why do we want better microscopes? Because microscopy is critical for the electronics that we all carry around with us, for medicine when we go to the doctor's office, for better thermoelectrics, better solar panels, pushing any technology, better vaccines. We really do need better microscopes. And not only better microscopes that can allow us to peer deep into the nanoscale. We have pretty good microscopes for that right now, but what we don't have is microscopes that allow us to see a functioning nano device or a functioning cell on all scales that we care about. And it turns out this is quite important, because if we want to look at electrons, current or heat or magnetism spins moving at the nanoscale, we don't have a good understanding. We don't have theories that can describe it. And so it's very hard for us to make the best energy efficient device that consumes less power, for example, so that your cell phone or any device can last longer without a recharge. So how materials behave, even in terms of their stiffness or elastic properties, are very different at the nanoscale than the bulk. And because of that, what we really need are a functional microscope that you can actually watch it and then build a theory, then work with engineers to design something that's more efficient. And we don't have those microscopes right now. We would love to have them. We'd love to be able to put a functioning nano device into a microscope and peer into it, watch if it got hot in one place and not another, or put a cell into a microscope and be able to zoom in, not kill the cell, and watch how these processes work, watch how medicines work better and do that better. We don't have these right now. So what do we need? What sort of illumination do we need to build a good microscope? So it turns out that if you do everything pretty well, the spatial resolution, or the smallest thing you can see, is going to be on order of the wavelength of the light or the electrons that you use to build the microscope. And so if we're talking about a nano device or a molecule within a cell, that means we're going to have to go to pretty short wavelengths, below the radio wave, the microwave, and the infrared that are all, macroscopic sort of wavelengths, and move below the visible to the ultraviolet, the extreme ultraviolet and X-ray region of the spectrum, because that is where the wavelengths are matched to what we're trying to see. And so we can use either a light or an electron-based microscope to do this. And this is just a picture of a microscope you might have used in high school, where you peer into it and you see a real image, and it is really fantastic. We can see things that we can't see with our eyes, but not at the deep nanoscale. For that, we need to use electron microscopes or X-ray microscopes. The picture of one shown here. And from a 40,000-foot view, a light microscope and electron microscope, the technology is different, but actually they both have beams. You need a beam of electrons or a beam of X-rays, and then they use lenses to focus the beam onto an object and then use another lens to make an image. And these microscopes, we can design them to work in transmission or in reflection. And so that's fine. And what's very interesting in my field and many other fields in science, for my colleagues here in the audience, that it takes 50 to 100 years to make a real technological change. That's what sort of, it can be scary, but reassuring that we sort of need long-term efforts in science to really overcome major challenges. So if you look at electron microscopes, for example, Thomson discovered the electron in 1897. And then in 1924, de Broglie postulated that the electron was small enough it could have both particle and wave-like properties. Then in 1923-ish, Davison and Gamer showed that yes, indeed, an electron wave can produce an interference pattern, showing that it really did behave like a wave and not just a particle. And then in 1926, Bush developed an electromagnetic lens, a lens that could focus electron beams and use them to build a microscope. And then in 1933, Ruska built the first electron microscope that had a resolution better than the best light-based microscope at the time. This is a picture of one of Ruska's microscope. And then it got the Nobel Prize 50 years later. So, and in the meantime, there was just a huge amount of tool builders, detectors, companies, applications to actually bring that microscope to what is now the modern electron microscope that's in every semiconductor manufacturing facility, in every good university worldwide now, and just critical for use. They are stunning. You can take a picture of a material or a biosample with a resolution of only a few angstroms to see individual atoms, which is amazing. There's a couple of drawbacks. There's no perfect microscope yet. The drawbacks, one of the drawbacks are that the high energy electrons that you use to make the wavelength really short so that you can see individual atoms, they tend to, any soft material, they will tear it apart, just literally melt it, turn it into organic goo. Now, fortunately, there is a way around that. That is freeze the sample. Plunge it to very low temperatures so that even if you break a bond, the atoms don't move. And that works stunningly well. In fact, it was many of the pictures we saw during COVID of the viruses and the vaccines were done using cryo-electron microscopy, because you could stick either the vaccine or the virus into a microscope. If it was frozen, if you broke bonds, atoms didn't move, so you got the full structure of viruses and vaccines. And this is one of our colleagues at UCLA that worked with Moderna to image the outside of the vaccine that was the modification Moderna had to make so it could be stored at regular freezer temperatures and not the deep freezer temperatures in the med school refrigerators. And another colleague at UCLA, Jiang Miao, developed special tomography where you take a sample and rotate it within the electron microscope and make amazing images of nanoparticles, really beautiful images of every atom in a nanoparticle. You could zoom in to small regions. And John made, this is not what you see in the microscope. It's a rendition of the data that you can get from the microscope, where this I think was a high entropy alloy nanoparticle, where they could split the nanoparticle, see every part of the nanoparticle, so they could tell all kinds of things. They could tell that, for example, at the nanoscale, annealing does not work the way people thought. To make materials that are have very good order, you first make the material and then you can you can heat it to high temperature to see that, to try to make it, find a recipe to make it go into the phase you want. For example, a magnetic material with very high strength. They found out that the theory of annealing was actually wrong at the nanoscale. And they also found that actually they could explain why some materials that had been theoretically predicted to be great magnets and very strong didn't actually work well because they weren't one particular phase of the material. They had many different phases. So these methods are amazing, but you would need 10,000 of these nanoparticles. If you lined them up, you could get to the diameter of a human hair. So the issue is they're amazing, but this particular study took 2 years. So you can only see a small part of the material and you can't see anything moving, because when they did the annealing study, they would take the nanoparticle out, anneal it, and then put the same nanoparticle back in. That's why it took 2 years, because they had to put it in the microscope, take it out of the microscope. That is a hard way to optimize a material. So that's why we want better ways of imaging at the nanoscale, so we can try to see things moving and such. So can X-rays help with this? X-rays, we've had X-rays around since 1895, when Röntgen took a beautiful image of his wife's wedding ring. And of course, they're used in your doctor's and dentist's office, and CT scans, many applications. For the most part, the X-rays that are in use, in widespread use, are essentially a better version of a light bulb. But the idea is still the same. Heat up a filament, generate electrons, accelerate them, and then make X-rays. So let's look at the history of X-ray microscopes. So in 1895, Röntgen discovered X-rays. Then in 1912, the Braggs demonstrated X-ray crystallography, where you shine a beam of X-rays on a near perfect crystal, and you get peaks, get light scattered that has the right pattern that then you can use to go back to what the pattern in the crystal is. It's really powerful. In 1948, Kirkpatrick and Baez made the first X-ray microscope that's shown here, or a version of it is shown here. Baez, in addition to this great demonstration, his other claim to fame is he's the father of Joan Baez. And many of you will know will remember that, or in the recent Dylan movie. Yep. Then in 1951, X-ray diffraction was used to uncover the double helix structure of DNA. As I mentioned previously, if you shine an X-ray beam on a perfect crystal, you'll get a characteristic scatter pattern that lets you take that and use some math and go back and show what the shape of the crystal is. But apart from that use, which is which requires a perfect crystal, if you look at all the other images that your dentist might stare at, or your doctor might stare at, or in the airport security, they're using really, really short wavelengths of light. If you look for airport security, 100 keV X-rays, so it can penetrate your baggage. That corresponds to a wavelength of 10 picometer. But there is no way that that image is anywhere near the resolution of the wavelength you're using. And this is because there are no good X-ray lenses. So we have the light, but we can't use that light to see very small things because there are no X-ray lenses, hard X-rays. And where even in the regions where we have some ability to make lenses, we can't make them good enough. So all X-ray microscopes were more than 10 times worse than they should be, and in this case, many orders of magnitude worse than they should be. So what can we do? So it turns out that to make a better microscope, we have to do two things. We have to throw out the lens because we can't make good ones. And it turns out we can't use an X-ray light bulb. We have to use a laser. And when we throw out the lens, we have to use an algorithm instead of the lens. We'll throw out the light bulb and use a laser. And if we do both those things, we can make a perfect X-ray microscope to really, and it can capture things changing. Okay, so let me explain first why it took so long, because we're just barely able to do that now. And this is well over 100 years after X-rays were first developed. So the challenge was that both of these things are technically very hard. In the case of a laser, it just takes too much power. We can't make an X-ray laser. If we want to make a laser at 1 micron, I can hold a laser in my hand and have a beautiful green beam, and I can power it with batteries. There's no problem. It is relatively efficient. But if I ask, instead of a 1 micron wavelength, if I want to have a wavelength of 1 nanometer in the laser or 1 angstrom, then the power requirement, a terawatt is about the electrical generating capacity of the United States. So we will never make a continuous wave X-ray laser. It just is not possible. It would take too much energy. And that's why I mentioned Star Wars era. That's why in the 1980s, there were proposals to shoot down missiles by making an X-ray laser based on detonating a nuclear weapon in space. Now, turns out that although, Star Wars didn't do this, they did do something else. They did learn how to make really powerful lasers on Earth that are now the outgrowth of which are the lasers that ASML uses to make the most advanced chips right now. So that came out of a spin-off from Lawrence Livermore and a company in San Diego. And that's also why the first laser light beam was demonstrated at 1.5 nanometers, was demonstrated using a completely different technology than laser technology, which is based on the population inversion by putting atoms in highly excited states. It was based on what's called electron accelerators. There's a picture here of the electron accelerator at Stanford that was used to make the first X-ray laser based on electron acceleration at 1.5 nanometers. But do you notice how long it is? This is the freeway interchange. So this is 2 kilometers long just for the accelerator part. And this year, 2010 was the 50th anniversary of the demonstration of the laser. So there was a lot of celebrations in DC associated with this. And it turns out Steve Chu, who is a sort of a laser scientist, was Secretary of Energy at the time. So he was lauding the X-ray free electron laser as a marvelous instrument, but Steve has a good sense of humor, and what he said was, but it wasn't free. And I should know it. It turns out there's about $2 billion to make this machine. So it's an amazing machine for science, but you can't build one at every chip fab or every hospital. It just won't scale. Now, people are trying to learn how to make compact versions of these electron accelerators using lasers to accelerate the electrons, but we're not quite there yet. This is already, the proposal for that was published in 1971, and we're still working on it. So it's, but we're making progress on other ways. And the other ways was to say, well, how would we take a laser where we have laser light and use another quantum physics to make shorter wavelength light? So the laser is amazing. I'm a laser scientist, so of course I love it, but it's actually amazing at how little it's progressed in terms of the wavelength. The first laser was demonstrated by Ted Mayman. Actually, Ted was an engineering physics graduate of CU Boulder. He demonstrated the first laser in the red and crimson. And in that 65 years, the shortest wavelength laser that's now in widespread use is the excimer laser. It's used to print a lot of our consumer electronics, the chips associated with our consumer electronics. And that has a wavelength of just under 200 nanometers. So there's less than a factor of 4 progress in the lasers we can build in that time. And the reason is the power requirement. So that's why quantum physics had to come to the rescue as what allowed us to make beams on a tabletop that one had some prospect of using in a widespread way. So this is not something that was predicted, but rather discovered by Charlie Rhodes working at the University of Illinois. So he was doing an experiment focusing a laser into a gas, and they saw 17 harmonics of the laser. And very soon afterwards, another lab saw more than 100 harmonics of the laser. So this has an analogy with sound. If you were playing a violin or a guitar and plucking the string, and you expect to hear, as you pluck harder, you expect to hear the fundamental tone and then the overtones and then higher and higher overtones. But nobody would expect to hear 100 overtones. So it was a similar situation. People thought, what could possibly make 100 overtones of light? And it turns out it's if you use a short laser pulse, it is the best thing possible that you can use to pluck the quantum wave function of an atom. So if you can imagine a laser distorting the shape of a string, or in this case, distorting the shape of the atom. And so it can distort it very quickly, and then that poor electron gets accelerated out in a boomerang-like trajectory, first away and then back to the atom. And then it recombines with the part of the electron that wasn't plucked out. And that essentially looks like so if I play this movie, it looks like it is the wave function of the electron, but it looks like a very exotically shaped string that then gives rise to, it has so many modulations, not just the fundamental tone and the overtone, but rather a very modulated string. And that is what radiates coherent light. And you can do that with a very, very small laser system. I mean, small, it can fit on the podium here as opposed to kilometers long. Okay, and it turns out it is exactly what you would design if you set about, we didn't, this was just a discovery and theorists figured it out later, but if you said, how would I make the Röntgen X-ray tube coherent? Well, in the X-ray tube, you heat a filament and boil electrons off the filament and then accelerate them in a field. And then when they decelerate in a target, they liberate their energy as X-rays. So in this process called high harmonic generation, the laser plucks part of the wave function from the atom, but that wave function starts in the quantum ground state, so it's very coherent. Then it accelerates it in a coherent field, and then it slams it back into the same electron wave function that wasn't ionized. So every step is coherent. So it is exactly what you would do if you said, well, how would I make a coherent version of the X-ray tube? And it turns out that what was needed is you have to be able to sneak up on the atom and pluck the electron before the atom realizes the electron is gone. I'm sort of, and so what you need is a light pulse that is comparable to the timescale of the electron response. And so it took a while, because if you go from a millisecond is kind of the time scale of a camera flash. And then if you use a strobe light, like the beautiful work of Edgerton, using a strobe light to capture a bullet piercing an apple. But then you have to go 3 orders of magnitude faster and 3 orders of magnitude faster and 3 orders of magnitude faster before you're fast enough to mess with an atom so that you don't completely ionize it before you can make that quantum sculpting that gives rise to the X-rays. So it took a while, and so that is why the visible laser was first demonstrated in 1960, but it took until 1987 to make short pulse lasers that could do the quantum sculpting and generate X-rays in this way. And now it's a very practical technology. I mean practical in R&D labs like NIST or in universities, and with some companies beginning to use them for some research and development. So we take a femtosecond laser, this is what it looks like, into a converter, and then make light at shorter wavelengths. Okay, so that solved the laser, the illumination. Now I want to explain how do we throw out the lens and still get an image. So we talked about how if you use a traditional X-ray lens, you're limited in resolution. And now I'll explain how we use a microscope without a lens to build a perfect X-ray microscope. Now, we know the reflected light from a sample, from a soap bubble, for example, can tell you the thickness of the bubble. So there's by the color. So we know we can tell a lot about an object by just shining light on it. Now, if the light is coherent, we can tell more. And so this is a little simulation from the PhET physics demonstrations here. What's special about laser light is that it has very good phase coherence. So what I mean by those words is that all the crests line up. In a light bulb, the light is emitted randomly from all parts of the light bulb. Now I'm going to ask Henry to do a little demo. Here, he's going to show, just shine a light bulb and a laser on the screen. He wasn't ready. No, I'm joking. Okay, that's the light bulb. And shine them both at the same time. And the laser. So what's the big difference? The laser is directed. Now, right, very directed beam, and that's because all the rays are going in the same direction. Now, and if we send those well-behaved rays with their crests all aligned through an object like a double slit, we can get a characteristic pattern that depends on the shape of the slit. And I'll ask Henry to just demonstrate that with a series of slits, 2 different slits, just to show that the pattern, you can tell the object from the pattern. You're doing the 2 diffraction gratings, Henry? That does not look like a diffraction. Ah, okay, do the other one then. That doesn't look right. Okay, thank you. Yeah. So there, you can see some of them. Good. So now the question is, from that pattern, how can we get back to this object or something similar? So let's do that with the OptiCAD. So now this is our object. This is the Professional Society of people doing optics and lasers in the US is called Optica, and the optical scientists, and this is the OptiCAD. Okay, so now we're going to shine a laser on the OptiCAD and then do a Fourier transform, which is what a lens does. So now I'm going to ask Henry to demonstrate Fourier transform by a lens, and the simple demo is to take an LED flashlight, and they've got a little square bunch of LEDs that where the light originates, and he's going to focus it onto the screen. Just show you how a lens takes a Fourier transform or makes an image. So this is just the little LED in the flashlight. You can see it with your naked eye if you look into one of your LED flashlights. So what the lens did was take that very diverging beam, and like in a microscope, we made an image of the object. And now let's see doing that with the OptiCAD. So now we've got our OptiCAD. We'll take a Fourier transform, but now we'll do it mathematically. And so you will get an amplitude and phase. And you can sort of see a lot of the similarities, so there's a little nose and round eyes. You can see there's circles on the amplitude. You can recognize a lot from the amplitude. And if we take a different cat, we will get a different image. And you can see this cat has X as eyes, and you can see X's here. And then this cat has round eyes, so you can see a lot of round features here. But you can definitely see there's the Fourier transform is different. Now we can also program this into an object, and when you shine light on it, it does the reverse, so we can go backwards. So now, Henry, are you ready to show the OptiCAD? Yeah, so those are the OptiCAD. And so all that is a little programmed phase mask to show that, and this is the basis of the things on the little glasses you can buy at Christmas time that shows that separates light, the Christmas ornaments into colors and such. Now, you might look at that and say, I can tell from this pattern, I can tell a lot about the object. But it turns out our intuition is wrong. Most of the information is in the phase. And I'll demonstrate that by showing a little inversion that Nick did for me, where you take this image, you take the Fourier transform of this image, you use the correct phase but the wrong amplitude, and you still get something that looks mostly like that object. So most of the information is in the phase, and that's what we're going to use in our microscope. So now what we will do, and just to show you that as another quick demonstration from our FET applets, this is something that Ariel did. So just very quickly, if we use a round object, and of course here we can do things that we can't do easily in a demo, change the size, and you can see the diffraction pattern changes. If I use a square, I get a square diffraction pattern. If I use both, I get a mixture. If I use an array, I can have it ordered and disordered, and you can see how the characteristic pattern changes. And then if I use an object, we call this the stick girl, and rotate her, you can see how the scattered light changes. So it is the power of interpreting that scattered light that gives us the ability to make a microscope without a lens and really improve imaging. So then going on from our stick girl to a real microscope, this is interesting again for how long it took. So the idea now with the microscope is we'll shine our X-ray beam on a sample, collect all the diffraction patterns, and then instead of a lens, we're going to use our algorithm to make the Fourier transform. It was proposed by David Sayer back in 1952, was first demonstrated in the X-ray region by Jiang Miao in 1999, and David is a co-author on the paper. So 50 years later, and this is the whole paper, and that did the proposal. So a lot shorter than what we have to write these days to be published, and also able to make very general statements that you would not get away with now. The extension to 3 dimensions is obvious. It was not obvious at all, at all. And now, to help the algorithms, what one can do is scan the illumination beam over a sample. And do you see how this is real data, so the diffraction patterns are changing. If there's a lot of overlap between the beam as you scan, the algorithm is forced to reconstruct the right image of the sample. So it really helps in terms of the ability to make a really good image. Henry was going to attempt. Henry, do you want to attempt to do this or not? He can try. He's got a circuit. He's got an IC circuit up there with a laser, and he's going to attempt to scan the laser over it, but I'm not sure how well this will work, but we'll see if he can do. Oh yes, look. So you can see there's 2-dimensional structure in the IC circuit. If he goes over different regions, do you see how the little pattern changes? He's wobbling. Okay. But you can see that there's different features that you pick up as you scan. And with these phase retrieval algorithms are now able to make really good reconstruction. So it's actually amazing. You look at the data and they look completely like blotches. And then you run the phase retrieval algorithm and you get these amazing images. In many cases, you would not think that you could ever recover a cell image from this kind of data. So they're, indeed, they are microscopes that do not use a lens, and that has all kinds of powerful capabilities in terms of being able to see very small things. And so now we are working with a whole bunch, we and others are working with a whole bunch of people who need better microscopes to see what they need to see. For example, 3M makes polymer metamaterials that are like organic materials. So if they put them into an electron microscope, they can melt. And so we're showing that we can use soft X-rays or X-rays that don't have too high in energy, so we can actually image the material without destroying it. And similarly with nanoelectronics or with NIST or with argon to develop better fuels and better combustion. This is a picture of the circuit that Henry was trying to scan. So it has multiple scale features, and of course the green light only gives you a pattern from the large structures. If you want to see the really tiny structures, you have to use a wavelength of light that's comparable to the structures. And in fact, to do that, our students had to build really complex scanning microscopes to be able to do all of this. But they were actually able to get an image of the sample both laterally and into the sample because X-rays penetrate. So that means that you can get an image of a sample without destroying it. To put this into an electron microscope, you would have to cut a piece out of the sample, but then the sample would be destroyed. You could make the image, but you couldn't test if it worked. So this is one big advantage of these X-ray techniques. The other thing we can do is see function, for example, heat transport, and that matters, as we know, because you can feel your computer or your cell phone heating up, isn't that right? And the clock rates in the computers have really not changed in over a couple of decades, because if they run them faster, they can't dissipate the heat. And because heat is hard to see at very small scales, this was an area we wanted to look at. And so this is how we look at it. We put some nanostructures on a sample, on an object, and then heat them with a laser to simulate a transistor switching. And then we probe with the X-rays because the X-rays can see very small things. So this is the laser heating, and then we probe. And the weird thing we saw when our students showed this to us, they didn't even believe it, and we didn't believe it for a long time. But what they found is that if you heat up nanostructures on a cold substrate, that if they were packed close together, they cooled faster than if they were separated. So that is weird. So that's saying, you've got a higher heat load, but they're cooling faster. And it took 6 years and many, many theories. But in the end, we figured it out. It's that heat flow at the nanoscale looks more like water flowing than heat spreading. So, water can be directed and then can spread out. And it's all got to do with phonon physics. So we figured it out eventually. But all of this is one of the reasons why it's hard to design devices that don't get too hot, because people, if you can't see how the heat is flowing, it's very hard to, you can make the device and then test its power consumption, but it's very hard to do it in an intentional way. So the last thing I want to show you is something with a hedgehog. So this is a magnetic texture that was predicted back in 2002, but the two theorists who predicted it, Han was telling me, they sort of used an average theory because they thought nobody would ever be able to see this. So what they predicted is that if you had tiny magnetic nanostructures close together, because these are all magnets, that the fields would interfere with each other. And so you would make these beautiful textures like a hedgehog. So this is a magnetic hedgehog where the spins are pointing in different directions, just like a little hedgehog. And so we did the experiment. It took 3 years because it was during COVID, and many, many, many students driving when we couldn't fly. But eventually, after taking several terabytes of data, this is for one 3-dimensional image, and 800,000 diffraction patterns, sticking it in an X-ray microscope at Berkeley, we were finally able to make the following movie. So what this is the little magnetic nanoparticles, and now you're seeing the spin texture superimposed. So you're seeing in the red and blue, you're seeing hedgehogs, which are spins pointing outwards, and anti-hedgehogs, which are spins pointing inwards. This has a connection to technology. This was just a useful sample for us to show the microscope worked. What we'd really like to do is look at these magnetic structures called skyrmions that can be used to encode memory or computing by very small currents. So nice energy efficient. And in fact, we've just begun to do that. So those are the hedgehogs and the anti-hedgehogs. And now we're just beginning to be able to do the same for our skyrmions. So this is a skyrmion showing the top of a skyrmion, the middle, and the bottom showing different types of spin textures. So with that, I'd like to end. So building microscopes of the future is not for the faint-hearted. It's a little bit like any technology. This is an example of NMR technology, which many decades after the fundamental physics was understood, this was the first variant NMR commercial spectrometer. This was this is technology that predates MRI, and if you looked at this little and blow it up, so building microscopes is very much like building NMR spectrometers. This machine is subject to breakdowns during periods of critical needs. It has a special circuit called the crisis detector. It senses your emotional state, and it then creates a malfunction proportional to the desperation of the operator. And keep cool, say nice things to the machine. Nothing else seems to work. And I think our students would agree. I think any of the students or anybody who works with technology in the audience knows this is the case. It breaks your heart before it works, but that's the nature of research. And so with that, I would like to thank the group and collaborators so much. I mean, they're the people in the lab doing the work. And thank you for your attention, and Leo for the opportunity.
Thank you, Margaret. So we have some time for questions from the audience. Yeah, please.
These projects take so long. How do you pick like the right target of like?
We don't. Yeah, we just try many different things, and we talk to a lot of people. So I had talked to somebody at Penn State for these little hedgehog structures, and that was Henry was the person who identified him. That was back in 2011, and then the paper. But that we didn't realize that we would have this other microscope back then. So we're trying to use a different method. So it really is very long-term relationships. Like doing anything hard is like that. You have to do it that way. And then students who can layer PhDs and go different places to different microscopes, so we are guaranteed some progress in any one particular period of time. That is a very tricky thing. So for example, when John first, did the first X-ray lensless image at Brookhaven in 1999, a lot of people told him there was no way that was going to work, or it was a very simple image. And for at least 15 years later, people didn't believe it, because the first images, we didn't have tychography, we didn't have fast computers. So it was, the images really were not very good. And so a lot of people thought that this is really not going anywhere. But then a lot of things came together, and often you find, advances are supported by multiple things happening at once. And that's sort of what happened, GPUs, high harmonics getting more mature, just all of those things coming, and then just the sophistication on which algorithm to use. So that is a question so people try to develop their scientific intuition over time, and then there's often just fortuitous discoveries like high harmonic generation. So it's really just being curious and willing to work with other people, I think.
So it's, a lot of persistence, love of science, but then some fortuity.
And some for exactly.
How do you pick the right stock market? Somebody picks the right one, somebody picks it. Plus a lot of experience as well in doing this kind of stuff.
A lot of fearless students, because, if you don't know it's not possible, you won't believe it. Isn't that right? Yeah.
Yeah, please.
Detectors, CCD detectors, because they were developed and perfected for astronomy, so very light sensitive. And then more recently, the faster detectors that are like the X-ray version of what's in your cell phone are becoming available, although they're not quite perfected yet.
You had a question?
One of the we want to do. Is there like a fundamental limit because with reduction in your wavelength, the momentum?
Yes.
Objects,
Yes. There might be a chance because, and the reason is that the wavelength one can use, or the photon energy is 200 eV, and that's still a whole lot better than 100 kV. So, and then you play tricks, you know, because the image is made up from interference of light from all parts of the sample, you can cover part of the sample to protect the delicate material and then put strong scatterers in another part. On the detector, you detect light as the interference from the two regions. So it's like an amplification process that you can see the scatter from a very weakly scattering object. Yeah. That's an ongoing project. That's another very hard project.
Other questions? Yes, please.
Ah, good question. It is, you know, 10 to the minus 4-ish, 5, 10 to the minus 5. But that means we can take you need about a microwatt to be useful. And so that is not a very big laser as lasers go. That means you need a few watts in the drive laser. And you can still have plenty to make images.
Please.
So sociology, how do you share credit if it's a lot of trial and error rather than laborious teamwork together?
Yeah.
Have a pact in advance that whichever one gets lucky, you're all on the publication, or how does that work?
Well, we do a lot of co-first authors, putting postdocs as last authors, you know, as they get more senior. And just the fact that in our field, you know, the number of authors is growing for just this reason, because nobody can do it alone. And it's, you know, that's very common for laser science, because if it's a new type of laser, you know, if you don't work with the application experts, it doesn't go anywhere. Because a non-expert, I can't do condensed matter theory, you know. So you probably can't align a laser, Leo, isn't that right? Yeah. So, you know, if we didn't work together, we
Not
couldn't.
anymore.
Yeah, anyway.
Funny application, all this accreditation dimension, it sounds like. That's interesting.
Well, you know, most of our students go to work in industry, so having industry collaborations helps them with a network, right?
But are you asking how the credit is shared and like if there's some application?
Yeah, maybe, I mean, publication is the academic version, but there's also patents and things, and just
Yes.
a lot of people work on dead ends. If those people did not work on all the dead ends, the lucky one wouldn't have gotten to the.
I see.
Right?
Well, so the patents are the one things that you're sort of doing in advance because it's an idea. And so it's the people that the author list is much shorter, right? Because it's the people who did the theory and came up with the idea and stuff and such. And so then the papers are longer because you need a sample, you know, if it's an idea on a new algorithm, then it's a very small number of people. But then it is still great to use that new algorithm to do something. And that paper could be much longer, could have a much larger set of authors.
Okay, I think with that, let's thank Margaret again for wonderful talk.
Yes.